bienvenue à tous après ces petits problèmes techniques. On va pouvoir commencer. Donc, on a le plaisir d'accueillir aujourd'hui Laura Kanzler, qui est CERMA de l'Université Paris-Dauphine, mais voilà, qui est maintenant avec nous. Et elle va donc nous parler d'un travail sur l'approximation quantitative de fluides pour les équations cinétiques avec croissance lente et plusieurs invariants. Je traduis comme je peux. Et je ne sais pas, will it be in English? Or...
En fait, je sais, il y a quelques personnes dans les salles qui parlent anglais, also, qui ne parlent pas en français.
Yeah, so
on peut faire ça en anglais, mais s'il y a un problème, bien sûr, on peut faire ça aussi en français, si vous voulez. So yeah, but just general, so I switch to English now. Thank you very much for the introduction and also for the invitation to the seminar. I'm very happy to be here, and I'm also very happy to join the lab soon in November. This is the reason why I'm still here for Phoenix Ring. And for a subject, I decided to present today a work which I started during my postdoc, which I did in Séminaire, and this is a joint work with Émeric Fouan and Clément Moreau. And it's about fluid approximation, so like hydrodynamic approximation of kinetic equations, probably with non-standard properties. So for example, equilibrium, which are decaying slowly and which have like several invariants. Okay, so maybe next slide. So.
Clique sur le PDF. Clique et ensuite tu
okay.
Yeah, so like of course, like this is what a general audience I know, so this is why I start with motivation and a little bit of a historical overview.
Sorry.
Before I really go into some sort of like our contribution to this. So, but yeah, so now the next the next slide. So what's the setting actually? We look at the kinetic equation. The kinetic equation is given here, where F, so the solution F is the density of particles. And each particle is represented by its position x and its velocity. And so this equation describes the time evolution of this ensemble of particles on a like kinetic or mesoscopic level. So you do not look at each particle, but you look at some sort of like the density which is given by. If you look here at the left-hand side, it's just the free transport operator, which just says that like every particle is transported along its velocity and just goes along its velocity and is heavy. But here the left-hand side, the right-hand side, there is an operator L, which is the thing where things actually happen. So this can be like a collision operator. So basically particles meet and collide and separate with post-collision velocities, or like a scattering operator, so if the particles collide with a background, for example. The important thing for this expose is that it's linear. And it's just acting in the velocity variable, so it's invariant in this. And moreover, what we assume is that the null space of L is spanned by an equilibrium. So like if you want, this is like a steady as like a
Excusez-moi, vous avez une baguette.
Okay, so so like it's spanned by this equilibrium M, so it's basically like L of M is 0. And moreover, this operator L admits the following conserved quantities. So basically, like if you multiply this L with either like 1, so like the 0 moment, the first moment V, or like a normalized, let's say, second moment, and you integrate it over the velocity space, it will give 0. So this will give rise actually to the following conservation laws, like the mass conservation, the momentum conservation, and the energy conservation, because like the mass of course, like the particle system is defined like this, just the integral over F over the velocity space, the same as the momentum and the energy. So the energy here is normalized in a certain way, but it's just details. Okay, and now just to give you an example of maybe the next slide, to give you an example of what kind of like operator you should imagine here. It's actually here, this is a BGK operator. And this BGK operator are quite nice to study like the basic behavior of an equation. For example, if you consider the Boltzmann equation, or the linear Boltzmann equation if you want, the basic dynamics is that you have a mixed value, which is like the steady state of it. And the dynamics will drive you towards like the local equilibrium, which is basically just in place. Okay, I will write it actually down. So like because I need it later. And although it's quite simple, it's just like relaxation towards an equilibrium, but it exhibits all the properties you want to investigate, and it's like some sort of like a simpler version of the equation you want to study. Okay, so here you have like a collision frequency, which is denoted by nu, and then you have here the macroscopic quantities of the solution F, so the mass, the momentum, and the energy. Equilibrium. And then you have here the loss. Okay. So what does this mean actually? If here you have the loss term. Okay. This means just the particle collides with a specific frequency which is depending on v. So you lose some sort of a particle, and it enters the system again in this shape. So basically, its new velocity is drawn from this equilibrium. And basically, here you just have it represented by its macroscopic quantities. Okay, so this is the macroscopic part. So also depending on F, the macroscopic part of your solution F. So this is basically what it means. So then what we want to do is actually we want to derive a hydrodynamic limit from it. So what does this actually mean? So maybe I have the next slide. This is actually part of Hilbert's sixth problem. So like the second part of Hilbert's sixth problem. Namely, Hilbert, in his like famous conference in 1900, his sixth problem, he asked the question, okay, can we mathematically put rigor to the axiom of physics? Meaning, if we go from the macroscopic state, like a bunch of particles which are interacting, to the mesoscopic state in a rigorous manner, which is the kinetic equation. So this is something which is not the hydrodynamic limit. This is like the Boltzmann limit, which is behind. And then can we go from this kinetic equation rigorously to the hydrodynamic equations, meaning to the evolution of the macroscopic quantities of the system. So you do not look at the whole density of particles, but you just want to know what does the macroscopic quantities, so like the mass, the momentum, the density, the energy. And he said, so like the idea is basically if the collisions of the particle are very, very fast, very, very frequently, not fast, very, very frequently, actually it is like F is expected to converge to the local equilibrium, which is basically given by this almost immediately. And the idea is then we can approximate our solution F by just its macroscopic quantities. So now we need to search like equations for the macroscopic quantities. So maybe the next slide. So what does this mean, some sort of like mathematically? So very fast collisions means basically there is a thing called the Knudsen number, which is basically this fraction like the mean free path or a typical length scale of the system. So the mean free path, like a particle travels without any collision, is some sort of like the mean free path. And this is assumed to be very, very small. And this uses a scaling parameter. And you basically like zoom out in space. And then you also have to like accelerate time. Okay. So this time acceleration here is given by at the moment I did not define what gamma epsilon is, but gamma epsilon will converge to zero if epsilon converges to zero. And then you rescale your equation, and the equation looks like this. It's just rescaled, and if epsilon is now the solution of this equation. And of course, like if epsilon goes to zero, if the collisions are more and more frequent, we, as I said before, expect that F converges to basically this quantity. And now the question is like, what are how can we describe this macroscopic quantities? So the rho, the m, and the theta with the mass, the momentum, and the energy of the system. And also an interesting question is like, okay, I mean, here I did not really define what this is, how we scale the time. But it's also like part of this limit to find a significant time scaling for finding this macroscopic limit. So maybe the next slide. Yeah, so like just to give an example, I mean, we are by far not the first ones looking at this, far not. And here I wanted to give you an example for linear equations. So this was done, for example, by Ellis and Pinsky in 75, or also by Goltz and Livermore in 2002, where they had the linearized Boltzmann equation. The linearized Boltzmann equation has an equilibrium of that form here, so that's a Gaussian. And if they do the following rescaling, and here you see already the typical parabolic rescaling, so epsilon squared, and then they pass to the limit, they find the following equations or the following system of equations for the macroscopic quantities. This is the so-called incompressible Stokes-Fourier system. So here you have like a diffusive equation for the momentum with pressure gradient, and here you have like the theta. So like the energy, and here you also have like a diffusive equation. And this here is the incompressibility condition. This is the so-called Boussinesq relation, which connects like theta and rho. This is why there's also no extra equation for theta, because just a problem like this. No? And of course, like this equation are basically the most simple macroscopic equations you find. So they are not the Navier-Stokes equations, but they are, if you want, they can be seen as a linear version, a linearization of the Navier-Stokes equation. This is kind of like natural because it said we start from the linearized Boltzmann equation, so we're here in a linear framework. So okay, so now maybe the next slide again. Exactly now, so there are some questions because like what is if not as in the case of the linearized Boltzmann equation where the equilibrium is a Maxwellian, but what is if the equilibrium is given by something like this, so like by negative power law. So it doesn't have like exponential decay, but like just some algebraic decay. So here this notation I use a lot. So this is it's called a Japanese bracket. The important thing is like it has the decay of, in this case, minus c plus alpha, but still it's not singular. It's an important point. Or also, I mean, like this equilibrium, the question is not, okay, does this equilibrium have exactly this form? It's just like the decay at infinity, which is here important. Okay, so basically the setting is the same, but now we have an equilibrium like this. Yeah, and moreover, for example, the linear Boltzmann equation, it has a spectral gap. This is something which is quite known. But now actually we want to understand, what happens if it doesn't really have a spectral gap, but if it just has like a spectral gap with a specific weight. So basically here you cannot do this for a CPT estimate. You have to put a specific weight given by beta in order that you can get your recursive estimate here. Okay, so beta is basically here a rate. So beta should be greater than -1 in general, greater than 0 is the important range here, because if it's if it's 0, then basically you have a spectral gap. So that's the thing. Another way to look at it is, okay, like my operator L does maybe not have a spectral gap, but actually if I weight it accordingly with this beta, then this weighted operator has a spectral gap. So this is also a thing which we want to consider, an extension which we want to consider. Okay, so now the question is like, can we, in a quantitative manner, so not so really like with estimates, pass to the macroscopic limit for an equation like this? And yeah, for this, maybe the next slide, which gives you some literature overview. One thing I would like to say straight at the beginning, this list is far from complete. But I think I wanted to point out the important points here in order to make some sort of a complete picture. I would start actually the list quite at the beginning. Namely, if your equation has like one conserved quantity, basically the equation conserves the mass, then this question was actually raised already for like algebraically decaying equilibrium. This question was already raised in the 70s. And then also there are these two papers by Vigo and many co-authors who answered this question, and found in the limit diffusive equations, but just for equilibria with quick enough decay. So found like diffusive equation as we expect for quick enough decaying equilibrium. But then, like the first time something non-standard was some sort of found was actually by Millet, and also in this paper Millet, where they introduced a so-called moments method to also include higher singularities. So like if the decay of the equilibrium is not sufficiently small, but you can go a little bit further above. And then they found actually fractional diffusion equations in the limit. So maybe let's keep this slide with the literature, but just to give you a little bit more intuition on this. This doesn't fall. Yeah. So let's take this BGK equation again. Okay. And I said, okay, normally, so like, let's say like this, case M is a Gaussian. Yeah? So what happens? You start here with a particle, so this particle collides with your frequency here, and your M is a Gaussian. Yeah? So what happens? Your particle basically goes along with its velocity, then it collides, then it takes another velocity, then it collides, takes another velocity, and so on and so forth. And then you end up with something like this. But now if M is something as brightly decaying, what happens here is you have your particle, it goes on with its velocity, then it collides, then it goes on with its velocity, collides, and so on. But then suddenly, because it has a heavy tail, suddenly a very big velocity is chosen. And then you end up here. And then it collides again. Sorry. And then suddenly, again, a very big velocity is chosen, and then it ends up here. And this, of course, like if you zoom out and look at this particle, like look at a bunch of particles macroscopically, of course, there's some diffusion happening here, right? While here, this looks rather like a Levy flight, yeah, which encodes, of course, like a fractional diffusion. So this is a little bit the underlying reason, some sort of, why we expect here fractional diffusion equations in the limit. And that was some sort of the first time discovered by these two papers from a PD point of view, and also from a probabilistic point of view a little bit earlier by Jana and Max. And one thing which I would like to mention, they introduced and used the so-called moments method, which is a very nice method, but the point is it's based on compactness arguments. So there is nothing quantitative in it. Okay. Then, of course, for very different kinds of equations with very different difficulties, that was investigated. But like I would like to point out two more papers, the one by Bourg and Beau, which is quite recent, and even more recent by Deschiche and Cruel, where they used a spectral approach to solve this problem. So they did not rely on the so-called moments method, but they have a spectral approach. And they also like included the difficulty of a lack of spectral gap, which I explained before. Okay, so but here that was all just for like one conserved quantity. Now, if you look at the situation where our system has like more conserved quantities, for example, the momentum and the energy, of course, this also has a long story if you think of the history of the Boltzmann equation. For example, L-Simplicity did it for the linearized Boltzmann equation. That was the example which I brought in before. As well as, of course, Bardos and Bukai. They also have like quite a contribution there, and of course, one has to mention was Salomon with their complete derivation of the Navier-Stokes equation from the Boltzmann equation. Moreover, quite recent paper also has like a unified, also spectral approach to this with the nonlinearity by Chevy and Loss. But for the case where they consider like some sort of algebraically decaying equilibria, the only, to my best knowledge, the only reference I know is the Hittner and Merino Zituna from 2016, where they basically proved the macroscopic limit exactly for this BGK equation with equilibria like this. And they used also the so-called moments method, which is not a quantitative method. So now with this tiny contribution, we would like to understand, can we have like a general understanding in a quantitative manner for equations with several conserved quantities, probably with equilibria of this type, and probably with a lack of spectral gap. So this is a little bit the thing which we wanted to understand. So yeah, and for this, there are some ingredients necessary. The first thing, we want to construct fluid modes. So now I would like to explain what fluid modes are. So first, yeah, first, what I would like to mention is like this whole approach and this whole proof is highly inspired by the old work of Alice and Vincent and by the work of Bois. So like this spectral study of the generator actually of our equation. Okay, so now what are fluid modes? Let's just start from the beginning. Let's start actually with just a reformulation. So we introduce this function h, which is just f over m. The reason for this is because everything will be proportional to m. As I said, we expect our solution f in the limit to converge basically to the macroscopic quantities, which is proportional to m. So it's quite natural to do this reformulation. After the equation looks like this, it's basically the same equation, just now everyone in every L2 now we have to put this weight m. Okay, so then we do this rescaling, which I was talking about before. And after our equation looks like this. Also nothing really happens. And now we do the Fourier transform, but just in the spatial variable. So we leave all the other variables completely untouched, but just in space we transform it via the Fourier transform. And after the equation looks like this. So here there are some notations, so maybe this might be a little bit much notation. So we have here the xc, which is the spatial Fourier variable, but we actually use the sigma, which is the frequency. It's just like the norm of this thing. And then we rewrite the right-hand side like this. So this is actually part of the transport operator, which was here. So this in Fourier variable is like looks like this, and now on the other side. And here we define eta as epsilon times the norm of the sigma. And now you have to think not epsilon goes to 0, but eta goes to 0. Okay? And here what you have on the right-hand side, this operator, so I call it L eta. And if you look at it, you can see it actually as a little perturbation of this operator L. Okay. So you have this operator L, which is known, which you know, and then you have this tiny perturbation, which comes from the transport with this eta in front. And now we look at the corresponding. So to this equation, you can affiliate an eigenvalue problem, which you can see here. So this eigenvalue problem, this is just the adjoint of this operator L eta. And now we are searching for eigenpairs phi eta and mu of eta, which solves this eigenvalue problem. But here you can also see that we incorporated this weight here. They incorporated this weight here, which comes from the spectral gap. So we need this weight for having a spectral gap. Okay. So and before I say so now, okay, like we started with our equation, now we end up with a random eigenvalue problem. Before I tell you why we end up with this random eigenvalue problem and what's the interest of this, I would like to tell that now we're interested basically in the spectrum of this operator L eta. And this operator L eta is just a tiny perturbation of this operator L. So we know the spectrum of the operator L. The spectrum of the operator L is this. So the spectrum of the operator L is generated. So this is the kernel. It's generated by 1, so it's 5-dimensional. The kernel of L. It's generated by 1, b and b squared, but I take some normalization. Doesn't matter. Okay, so this is the thing. So it has eigenvalue 0, which is 5, which has algebraic multiplicity 5. And these are basically the 5 directions. So you can always think V is in R3. Yeah, one tiny comment. I wrote everything here in RD, but normally like D is equal to 3. This is the reason for this. Okay. Yeah.
How can you say that eta is very small with respect to 1? It means that you do not consider large frequencies.
So I consider this. So I do here. This is the funny thing about it. I have here this equation, and of course, I also have here big frequencies. This is really normal. But to every frequency, I associate an eigenvalue problem. Yeah? This holds for every frequency. So the frequency here is fixed. So that's the thing. So if I look at this eigenvalue problem, this is a constant. Okay, and this holds for every constant. Okay.
Okay, no, the question was data epsilon times modulus of psi.
Yeah.
Which is small with respect to 1, it means that psi is not too big.
Indeed, but the thing is, like, look at the limit epsilon goes to 0, and this
Yes.
for and this for a fixed side. This is fixed. In
It's fixed, so
This is fixed. So that's a little bit the point. I associate to this equation for every side. I associate. So if you want, here there's implicitly this stands on one side. Okay, implicitly. So I actually would need to write like a side here, but it's the same for everything, so it will not affect it. Yeah? So really, in this configuration, this size is. So that's one. So, but the point I wanted to make before is like basically, okay, now I investigate the spectrum here of this operator L. I know all the spectrum. So it's basically here, these are the eigenvectors, eigenvalue 0, 5-dimensional. But now the question is like, how does this change if I perturb it a little bit here? Okay, so that's a little bit the question now. Okay, next slide. But before I want to tell you how to solve this eigenvalue problem or how to investigate the spectrum, I would like to tell you why we actually need this eigenvalue problem, because it might seem a little bit random, but I would like to explain this now. Okay, so this is our eigenvalue problem. So how can this be useful for passing to the microscopic limit? So we expect basically like this macroscopic quantities of our solution to converge basically to the microscopic quantities of the limit system, right? So in the end, we want some sort of to get an equation for these macroscopic quantities, okay? And for this, we use our eigenpairs. So suppose we found some eigenpairs, so mu eta and phi eta, and then we have our equation. And now we test the equation against each of these eigenfunctions times m, okay? And if you do this, and then of course we integrate over the velocity space. And if you do this, we basically end up with this. Here I did nothing but like using the equation. Huh? So here I have the right-hand side, fine. And here I just put the L to the fluid mode, which is now the joint of the fluid mode now. And now I see here, but look, I know what this is because it basically solves the eigenvalue problem. So then I just use the eigenvalue problem and can write it like this, okay? So here I just use the equation. And now I remember that I can write our solution H as the macroscopic part times the so the rest. This is the orthogonal part to the microscopic part. So this is this normal orthogonal decomposition of it. So basically use it, plug it in, and after I do this, I get the next slide. Here, yeah, exactly. So I get for every eigenfunction, I get basically an equation like this. And here on the left-hand side, you see, okay, here I have the time evolution of my macroscopic quantities multiplied with some vectors. So these are just integrals of this fluid mode or of this eigenfunction. And on the right-hand side, I also have like the macroscopic quantities with some like constants. So basically this will converge to constant. And then I have, of course, some error which is depending on some sort of the microscopic level. So hopefully this will converge to 0. And here I have not only like one eigenfunction, but I will have like a bunch of eigenfunctions. So in the end, this will be a whole system for the macroscopic quantities. Yeah? So this is how I use basically this eigenvalue problem to derive the system of the microscopic quantities. And then there's one important thing which I would like to point out, which is quite important. Here you see the time scale, which at that moment I did not choose yet. It's just a gamma of epsilon. But on the right-hand side, we have the eigenvalue. And in order to make this limit meaningful, significant, they need to be of the same order as epsilon goes to 0. So just a little reminder. Sorry, I think I put it here. So eta is the frequency, as the norm of the frequency, which is fixed times epsilon. Okay. So the thing is, I need to choose my time scale according to how the eigenvalues converge to 0 as eta or epsilon goes to 0. Otherwise, if I want to do a limit here, this doesn't make sense. Okay. So that's here the important point. And I write it also maybe here. So my gamma of epsilon should be like my eigenvalue of epsilon. Okay, so that's really important. Okay, so that was, I hope this motivated you, that it's very interesting to basically look at this eigenvalue problem. Okay, so maybe the next slide. Exactly. So now I hope that I convinced you that this fluid modes, or that searching for eigensolutions of this eigenvalue problem is interesting. So let's discuss a bit the existence. So if there are actually solutions. Okay. And the thing what I want to show you here is basically very much following the old work of Alice and Pinsky, which is I think very beautiful, although hard to read. And we start, okay, so this is just our eigenvalue problem, okay? And in order to solve it, I use a specific assumption of my operator L. So this assumption, I have to admit, I need. Namely, I assume that L tilde, so remember L tilde, I mean, this is just a technical detail, but basically L is basically this weighted L tilde. So this L tilde has the spectral gap. So that's a little bit the point. Okay. Anyways, it's just let's say my operator L weighted has to have this form. Okay. So on one hand, it should consist of a compact operator K, and then it should consist of something which is nice. So here I wrote one, but whatever nice function without any singularities and without any trouble is fine. Yeah? So like basically it should just morally have this form. Yeah? And then I can further decompose the operator K into the projection P and basically the rest. Okay. So this is the projection onto the finite dimensional part. Basically the projection here, which is basically also on the blackboard here all the time. And then S is the rest. It's just what's not in the projection. Okay, and the important observation here is, so assume this operator K is compact, so this is a projection, so S for sure has to be compact. And now, using this decomposition, plugging it here, like in this formulation here, doing some algebraic reformulations. So really from here to here, not much happened apart from rearranging terms. I end up with this formulation here. Okay, and now you can already see half something beautiful. Why do I say half something beautiful? On the left-hand side, you have the finite dimensional part of your phi, with some multiplication operator, which is not that bad. And then you have like an operator which involves S, which is a compact, nice thing, and also some multiplication operator, and phi. So if this violet thing here is invertible, actually something very beautiful happens, because I can characterize my solution phi just by its finite dimensional part. And indeed, so maybe the next slide. Yes, this thing is invertible. And this the proof for this works because of the compactness of S. I mean, it's something to prove. I will not detail this out, but yeah, one can show that this operator is invertible because S is compact. So what you can do is you can put it on the other side, and you can describe phi just by some operator, depending and just depends on the finite dimensional part. So yeah. Exactly. So like this is I call this operator G. So basically it's just this just put on the other side. And the important thing here is this G is just depending. I mean, of course, it depends on theta and the eigenvalue. It depends just on the normal V and V in one direction, in the direction which is sigma. And remember, sigma comes from the transport. So sigma is the Fourier transform of like the transport operator. So this is basically the direction, the Fourier direction actually, in which the particles are moving. So this is quite important actually. Okay, so now let's solve this, and we can like project everything now onto its finite dimensional part. So basically we multiply this equation by each moment, so by the zero, the first and the second moment, of course, with the corresponding weight. Then we define, so this is just a definition to have something not as big written here. We define C, it's just the vector of the macroscopic moments of the fluid mode. Now we ended up actually with solving this algebraic system, which is a 5 times 5 algebraic system. Okay, and now I want to know, is there a solution U and C to this finite, so 5-dimensional algebraic system? And remember, if we have C, then we also have the whole phi. So that's a little bit. Okay. And now this is basically equivalent to, is there a solution mu such that the determinant, so basically you just bring this to the other side, then it should be equal to 0, so that the determinant of this matrix here is equal to 0. And you can already see this smells very much like an inverse function theorem, right? Like you want to implicitly write, so you have this equation and you want to search a solution. Can you like basically construct around 0 a branch of solutions mu theta? Because you know it's at 0, everything is 0, it works because of you know how your amplitude operator looks. So that's a little bit the question here. And now the question is answered basically by this Sani proposition. So yes, there are exactly d plus 2, or if d is equal to 3, exactly 5 solutions to this. Which means so we have exactly d plus 2 eigenvalues, so 5 eigenvalues. Meaning that also this we have exactly 5 solutions to the algebraic system, meaning that we also have exactly 5. So that's a little bit. I will not go that much into the proof. It's quite technical, and as I said, like main ingredient is the implicit function theorem. But I would like to mention one thing, namely this 5 times 5 system. You can use symmetry of the equation, and then you can basically split it into one 3 times 3 system and a scalar equation. And then you show basically that the 3 times 3 system has 3 solutions, and then the scalar equation has 2 solutions, which give in total the 5 solutions you need. And why is this so important? Because basically with symmetry properties, and you use a lot that the operator G is just depending on equality, like with the transformation, you make this here, this V1, it's just V dot sigma. Okay, so it's just the direction of the movement of the particles. And these here correspond basically. So what does this mean? Here I have encoded in this algebraic system. I have encoded the 0 moment, so the 1. I have encoded the second moment, and I have encoded here one direction of my velocity space of the first moment. Yeah? And in this equation here, I have encoded the 2 other directions, which are orthogonal to sigma. Okay, so that's very important. So basically, I split my velocity to the direction of the movement and to a direction orthogonal to it. So this is basically what is okay. So this is the important step. Okay, so right now we know the following: we have our 5 solutions, we have our 5 eigenvalues, but as I told you, it's very important to know how these eigenvalues converge to 0. And at the moment, I know something like this, so not really much. There is, of course, for positive epsilon or for positive eta, there is a tiny circle around 0 where there are no eigenvalues. Yeah? Because like if eta is 0, then all the eigenvalues are 0. If it is positive, there is a tiny neighborhood around 0 where there are no eigenvalues. As you have the spectral gap, which prevents you to hit the other part of the spectrum, and then you have your spectrum. Okay. So, but more now the thing is, like, can we know a little bit more about it? Because especially we need to know how this eigenvalues converge to 0. So, and this is answered by yes, we can, just using symmetry properties of the system. Okay. First of all, we can choose this normalization of our projective part, like of the macroscopic part of our Bluetooth. This is a choice we can do. Then what else is also quite important? We know that the macroscopic part, so this is just the orthogonal to the projection, will converge to 0 as the real part of the fluid mode. So importantly, it will converge to 0. So that's important. This also gives quantitative estimates for the whole method. And then we know the following: we can actually distinguish the eigenvalues, and that's I think actually quite beautiful. So there is one eigenvalue where I can show that it's real. It's called Boussinesq eigenvalue, and Bloom this is 5. This is the eigenvalue. You know it's real, so this follows from symmetry properties, and this is one of the 3 solutions of this 3 times 3 system after the equation. So it has The fluid mode, you can approximate it at 0 and has this shape. So it has something of the 0 moment and something of the second moment, but it doesn't have something of the first moment. Okay, that's also quite important. And then you have the two acoustic waves, which are the other two solutions of this 3x3 system, which you can extrude. Yeah. And you find that they are inverse or like negative complex conjugates from in the sense of if you complex conjugate the one and put a minus in front, then you get the other. And the same holds also for the fluid modes. And what you see here is you have like the 0 moment, you have the second moment, and then you have also the longitudinal part of the first moment, meaning exactly the separation here, what I was talking about. And this is why they're also called longitudinal directions, because they're going in direction of the movement. But then you also have the transversal waves, which are also real. This is also important. And they go in the two transversal directions of the movement. So they basically go in the two other directions. Here again, I took the D. So this you can see, and this is actually quite nice. But then we want to see more, namely, also like how do these eigenvalues scale? So that's actually a very important question here. And you see it in the next picture. So this is basically how the spectrum looks like. So I will first discuss basically the thing which is called diffusive regime. So alpha, remember, alpha is the decay of the equilibrium. So meaning alpha is greater than 6 plus beta, meaning alpha is big. So you imagine to be like in the standard regime, like as if you would have a function. Okay, so what you see here is, again, you have here your inner green circle with the eigenvalues, you have here your spectral gap, and then you have here your eigenvalues. And here, so you have 3 dots. And in this dot, there are actually like 3 eigenvalues. They are on one hand the Bose eigenvalues, so the 3 real ones. One hand the Bose eigenvalue, and the transversal wave eigenvalue. And here you have the 2 acoustic waves eigenvalues. And the important part that here is that if the decay of the equilibrium is big enough, they are all on the same. They all have the same behavior as eta goes to 0. They're all on the same scale. And the scale. So if alpha is greater 6 plus beta is eta squared, which corresponds to the epsilon squared, which is the usual parabolic scaling which we all expect. But if this is not the case, something very interesting happens. So if alpha is less than 6 plus beta, you find basically your 3 eigenvalues. So this is the Bose eigenvalue and the 2 acoustic waves eigenvalue. You find them at a scale which is not eta squared, but a bit slower. So they have this fractional scale. This is stolen. If in this regime, this is basically this is a little bit slower than eta squared. But the transversal wave eigenvalues, they are still faster. So either, so like if alpha is greater than 4 plus beta, so if alpha is between 6 plus beta and 4 plus beta, this goes like eta squared. And if alpha is even smaller, then even they become fractional. And they also become a fractional scaling, which is in any case fast. So this is basically the important message. And now I'd like to ask how much time do I have?
10 minutes.
10 minutes.
We started a bit late.
Okay, no, this is fine. So just some words about like how do you know this? Like how do you know? How can you some sort of like define how this eigenvalue scale? So we'll just try to outline this a little bit after. Maybe at next slide. So okay, with this. We again start with our eigenvalue problem. And the only thing which happens here is basically that we separate into its real and imaginary part. This is something which is a bit annoying, but since we are now in a complex plane, I think we need to do this. And in order, through this is what something which I did not tell about, is one can choose the projection, the real part of the projection is also the null to the imaginary part of the projection of this eigenfunction. This is just a choice you can make. And now, if you want to know something, for example, about the imaginary part of your eigenvalue, what do? You multiply this equation by the projection of the imaginary part, integrated over the velocity space. You do the same here with the real part, and then you add it, and then you basically shift something around. For example, you put this eta on the other side, and then you basically end up with this integral. So again, this is just like testing against the projection part of the fluid modes, and then you end up basically with this equation. You can do the same thing with the real part, and then you end up basically with this equation. Okay, and if we look at them now and theoretically pass to the limit, you see on the one hand, this will converge this integral evaluated at eta equal to 0, which is just an integral. Okay, but then here, if you do this here with the real part, you see this will vanish because this. So here you have a minus, here you have a plus, here you have a minus. So this will vanish, and this basically will actually converge to 0. So if you go to the next slide, so this is basically what I mean. So like the imaginary part really scales as eta in the limit, and the limit of the imaginary part over eta is just this integral, while the real part it scales faster than eta. I mean, it's also not that surprising since we actually expect the eta spread. So the thing is, there is some power of eta still hidden in the microscopic part of the fluid modes. Huh? Okay, so now let's get it out, so to say. Let's find out what eta is still hidden in there. So the first try is, of course, to do this reformulation. So you have here the microscopic part of phi eta, and you just write it as eta times the microscopic part of some other field, eta whatever. Huh? So you do the same. So here, here I just showed it for the Boussinesq eigenvalue. You can do this for every eigenvalue, but the Boussinesq eigenvalue, I mean, it's real and then it's easy. Okay, just do this. You do this transformation. You end up with these two equations, and now you let formally eta goes to 0. Okay, you know, because you know that this scales higher than eta, this vanishes, and then you end up basically with these two equations. Another question is like, does this make sense? And you know. And this is actually a question of integrability. So you know, basically out of the coercivity estimate, that you can invert this operator on M2 with this weight. Okay. So now we have to check if the right-hand side is in a 2 with weight beta and n. So it's really an integrability question. And if you look at this, here is a power 1 of v. Here you have the projection part of the eigenvalue, which has the highest power is v squared. So in total, you have here v to the power 3. You have to square it because you look at there are 2 norms, so you have basically 6. Then you have 6 plus beta minus alpha because the minus is m. Meaning, if alpha is greater than 6 plus beta, this makes sense. If not, then this doesn't make sense. As easy as it is. Okay. So meaning, if you do like this is a very formal argument, but if you do the corresponding estimates, you find the following: exactly that the real part of your eigenvalue scales is eta squared, and the limit is basically this integral. And one can also show, I mean, you might ask, no, but why is this not 0? One can also show because like the real part, or actually I know it's the imaginary part of the projection of phi 0 is 0. So basically this part evaluates at 0, and the integral is actually just given this. But this is a technical detail, okay? So, but yeah, that's just a little bit the idea of the book. And of course, like the first idea was like to try to scale an eta out of it. Why an eta? Because like then after you have an eta squared, which is the parabolic scaling which we used to do, which we are used to. But if not, if this is not given, so maybe the next slide, we'll have some integrability problems, and you need some truncation. So basically, you multiply your eigenvalue problem not only by the projection part, but also by this truncation function, which basically truncates after a very big value. Okay, and you do this, and basically what is needed here is some sort of double limit argument. Okay, so you multiply your equations, you add them again after integrating over the velocity space, and then you end up basically with this integral. So here you have an error term, which is of course depending on the truncation and of course on your eta. And the important part is that it goes to 0 uniformly in eta and in R. And then you have basically this integral, okay, with this truncation. And now the thing is, you do this magic coordinate change. You write u is equal to this power of eta times v. And why exactly this coordinate change? This is the reason for this. It's a little bit hidden here, but this is the only coordinate change after which you find integrals which are uniformly So their integrability do not depend on eta anymore. So you do not have eta in front of any power which influences the integrability of the thing which is in there. So this is just a very formal reason why exactly this coordinate change works. Okay. So after you do this coordinate change, you find these integrals. You find, okay, like they are integrable uniformly in eta. They are something finite uniform in eta. So you can pass so you know that this will vanish as r goes to infinity. If you choose now your scaling exactly as the factor which comes out after you do this coordinate change, you can pass to the limit, because this will then have order 1, the limit exists, and maybe you can go to the next slide. And basically, yeah, you have to choose this in order to not blow up or lose everything. And then you see basically that the limit, that the eigenvalue, the fractional regime converges as this to 0 to this basically finite integral with this rescaled eigenfinal limits. Okay, so this is just a little bit an idea of like how do you like scratch out scaling of these fluid modes out of your eigenvalue problem. Okay, so now I mean we finally can go to the macroscopic limit. So the thing which I promised you at the very beginning. So again, as I told you at the very beginning, we have our equation. We test it against each of our fluid modes. Now we know how they look like in the limit. We know how the eigenvalues, the corresponding eigenvalues behave in the limit. We remember, of course, this is also from the blackboard. And we end up basically with this system. So here you also see, I have here the mass here of the energy, and I split up the momentum in its three directions. So this is the longitudinal direction in the direction of the movement of the particles, and these are the two transversal directions. Here I also already put like the time scale on the other side. And here I have some sort of diffusion matrix, and here I have an error which can be estimated to go to 0 as the square root of the eigenvalue, which means as the square root of the scaling we choose. Okay, so this is where the quantity is. Okay, now the important thing here, the diffusion matrix looks like this. So it's block diagonal shape corresponding to also the split in these longitudinal modes and these transversal modes. So basically this here are the longitudinal modes, and here you have the transversal modes. Okay, and here there's some other things which will give rise, for example, to the pressure gradient. Okay, but the important thing is here the diffusive matrix. And you see this is basically what I showed you in the picture. We have here these two different scales. If the decay of the equilibrium is fast enough, I told you they are both the same, and they are both eta, so epsilon squared. But if not, then not. Okay, so that's here a little bit the problem. So what happens? You have to choose now your epsilon such that this limit exists. So you have to choose it as this lower scale, otherwise you will have a blow up in the other terms. Meaning, if there's really a scaling difference and this really goes faster than this, you have to choose your gamma like this scaling, which means that also this part in the limit will vanish actually. Okay, so this is just a very formal description, but basically you do this, then you pass to the limit, you prove that your error terms will converge to 0 quantitatively, with basically you can move more or less in a certain topology, which is also a bit weighted. Sometimes I don't want to go that much into details, but basically they go with gamma, just gamma. Okay, so that's a little bit different. Okay, and if you do this, you end up with your system for the Fourier transform variable. Then you have to transform back, and here, remember here you always have like an eta, the norm of eta, to some power, which can be eta squared or some fractional power, and this will give rise then to the diffusion and the fractional diffusion limit. And if you go on one slide more, yeah, here it's just to remind you that you really have sometimes these two different scalings. Yeah, that's the important thing. And if you go one more, yeah, exactly. So basically, in the end, you would have the following systems. So F will converge towards this. It's not a surprise. This is what we expected. And if you have enough decay of the equilibrium, it will converge to the normal Fourier Fourier-Stokes limit, where you have the diffusive equation for the mass, for the momentum, and diffusive equation for the energy, with the momentum also of the pressure gradient. And here these two things are like the business relation coming from the conservation of momentum is a constraint which you will get in the limit, as well as the incompressibility condition that comes from the conservation of mass. Then you end up with this system. But if not, if your integrability is not high enough, you'll end up with no diffusive thing in the momentum, because this term will converge to zero. But you will end up with a fractional diffusion equation. The energy cancels in the mass. And exactly. So that's a little bit the theorem which we can prove with this. And yeah, I think it's time already. And yeah, thank you for your attention. If you will, it's like more than.
Thank you. Are there questions? Des questions either from the remote audience or in the room? Yes.
Sorry?
Is there any hopes for the convergence to a estimate with respect to epsilon?
Yeah. So this is a little bit what I said. Like you can. The thing is, the topology. I don't want to go into this of the topology. So you have to weight the L2 norms accordingly, also with the weights coming from the fraction. Yeah, but you can. So this error term, which was on the slide before, you can estimate it approximately as gamma, the square root of gamma epsilon. So like it's epsilon if you have the normal degrees of scaling, and it's a square root of this fraction if you have the fractional scaling.
Other questions? None from outside, from the remote participant? 2, 3. If not, we thank you again.